Hello. How's everyone doing today? That sounds good. Hope you're enjoying reInvent thus far. It's a great Monday, great weather down here in Vegas. You're here at MOB401. This is 10 tips and tricks for improving your GraphQL API with AWS AppSync. My name's Michael Paris. I'm an engineer on the AppSync team, and recently I've been working a lot on a new set of client frameworks and tools called Amplify. We're going to talk about GraphQL. Given that it's a 400 level class, we are going to get a little technical. There's going to be some code on the screen. Hope you enjoy that. We have a lot to cover, so I'm just going to dive right in. So here's our agenda. I said 10 tips. It might be more than 10 tips. I'm sorry about that, but we have 10 topics. First, we're going to cover schema design. We're going to go over some data design, which is more database-related stuff. We're going to be talking about leveraging AWS Lambda. We're going to be talking about real-time data, some rapid development techniques, offline data and use cases thereof, continuous integration and deployment, operations and monitoring, testing your APIs, and finally, we're going to end with schema governance, which is something I almost always hear from customers as they're adopting GraphQL. So first things first, we're going over schema design. So every time I start talking about anything GraphQL, I generally start with the schema because it's really the most important part of any API. It impacts pretty much everything else that you do from the client to the backend. It's going to impact how you query your data. It's going to impact how you read data. It's even going to impact how you communicate what your API is able to do to your developers and to your customers. So the first thing is use long descriptive names. This is tip number one. The reason why is that every GraphQL API has unique names. You can't have name clashes, and there's no namespacing concept in GraphQL. So to get around this, you have to have long descriptive names that are not only unique, but are informative to your users to tell you what data that thing actually represents. It's a pretty common use case to have an API that fronts multiple backend resources. Maybe it's different services, maybe it's just different data stores for the same service. And it's not abnormal for those backend data source or services to have similarly named data. You could think you might have two services. Both of those services might have a user concept, and they might both name them user, because when they're building them, they build them in a silo. And then when you're exposing them, you need to figure out a way to expose both of those user concepts with a unique name. So tip number one, use long descriptive names that adhere to a pattern. It's pretty common in AppSync to see people proxying AWS APIs. So this is something we see often where they'll come up with a convention. And you'll have a service prefix and a type postfix. And then if you stick by that convention and you adopt that early on, you're going to have a much better time and be able to build much larger and more evolvable schemas as you go forward. The next thing we're going to talk about are input and output patterns. So developing a pattern for inputs is one of the first things I recommend you do in a schema. You might have, in this case, you see a create user post mutation. It has a single input field named input of type create user post input. There's a few reasons for this. The first is that it makes your APIs more resilient to change. You don't have to go change all of the arguments of your query and mutation fields, which are pretty important every single time you want to add a field to a type. And also from client perspectives, it maps really well to how you build client applications. When you're trying to operate on an object in a front-end app, you're often trying to operate on that object. And if you have a destructured input, and you have, instead of just one input type, a bunch of input fields on this mutation type, you're going to have to destructure that object every single time you want to operate on it. So this, I would say, I definitely recommend doing off the bat. Now, as it comes to output patterns, this is one I've seen go both ways. So as you grow, I find that this is a really useful concept, and it might seem unconventional, but it allows you to do some pretty interesting things. So in this example, we still have our input, we have our create user post mutation, but instead of just returning that user post, we're going to return this create user post output. This pattern was first popularized by Relay, which was an early GraphQL framework. And it allows you to do some neat things. And in this case, you can see we're actually giving a reference to our root query type in the output response. And what that allows you to do is basically do arbitrary reads after writes, which can get pretty powerful once you start using them. And here's an example of how you might use that. So here we've got a read after write. we're going to go ahead and call our create user post mutation field. We're going to create a post with the title GraphQL at reinvent. And then we're going to get back the user post and the title, which is the object we just operated on. But then also we're going to go make this arbitrary query to go query our user feed. So the reason you might do this is that not everything is so easy as just a flat list. Often in the front end, you can kind of get back that object and put it back in a row and be able to do that optimistic update on the client. But sometimes you need the back end to do a little computation before you figure out what is that thing. And this allows you to do both the update and get that updated response with that update taken into account in the same network request. The next pattern we'll talk about are pagination patterns. This is another thing that you just have to do off the bat. And there's no one-size-fits-all solution. And the way I'd recommend to go about it is to really think about what are your pagination requirements. There's different patterns for different requirements. And sometimes one pattern is just overkill for what you need to do. And other times it's not. So the questions you should be asking yourself are things like, do you need a cursor per item? The inverse of this would be having a cursor per page. And you can think about, I might be asking for 10 objects. And then if I had a cursor per page, I can get 10 objects, and then I can get the next 10 objects, but I can't get 10 objects and then get the next 10 after the first. So that's kind of the difference there. Another thing to think about is, do you need forward and backwards pagination? That's another topic. And then the last is, do the edges in your graph contain data? So the most common example, and one you probably have heard of, is if you have a social media application and you have friendships in them, you might have that isAccepted flag on the friendship itself. That friendship is really the edge between two user objects, and you can basically place information on that edge to build more powerful APIs. And we'll see how that looks. So here's a really simple pagination pattern. It's one that we use a lot with AppSync. It maps really well to DynamoDB. And it basically, it's kind of it's simple and effective. It allows you to get back a list of items, and then it provides a single next token. The tell for whether you have more objects in that paginated set or not is simply, is that next token null? If it's null, you're done. If it's not, there's more information to query. And it's that easy. You can see the user's posts field doesn't return a list of posts or user posts. It actually returns this user post connection. And then you'd have input arguments on that field as well, as we'll see in a minute. Here's how you might query that. We'd have a simple paginated query. It's going to call this list objects query field, and it's going to give a limit of 10, saying we want 10 objects. It's also going to provide a next token, which will tell us where in that set we should start paginating from. You'll notice that this is a cursor. So the next token, as you get it back, if it's null, you're done. If it's not null, you've got more items to read, and you can continue to paginate from there. Here's a slightly more advanced pagination pattern. This is one that introduces edges. So in this, we have not only the connection, we actually have the edge as well. So a connection is itself a wrapper around a set of edges, and this is probably more traditional to what you'd see in a graph database or a traditional graph, where an edge wraps not only an object, which we're here calling a node, it also has a cursor. So this is an example of where you'd have a cursor per object. But then you can see also here that we have that isAccepted flag on the edge itself, so that we can put data on the edge between two associated objects. We're also going to introduce this page info concept that allows us to give more advanced information about the pagination itself. In this instance, it just has the has next page and has previous page. And the reason for that is that this is actually going to also allow us to do bidirectional pagination, so that we can not only go forward through a set, but we can move backwards through a set as well. We're also going to add things like count that you can use as well. I've also seen people add things like aggregation queries on things like this. So you could put aggregations on a connection. And do, if you were using Elasticsearch, for example, you could do aggregations on the edge associated with a user. You could get the most views by user, for example. And here's another example of how you'd use that. This is going to call the list objects field again. We're going to have the first 10. We're going to call it after now instead of next token, because we're doing a forward pagination. You can also, in the inverse, you could say, give me the last 10 before, and then that would do the reverse pagination and move backwards through a set. So the pros of this are that you can paginate pretty freely. You have a lot of flexibility. The cons are that it's going to add a lot of overhead, both to your schema and also to your clients, because when you do things, if you're going to do things like code generation, you're going to see these edges in this code, in the code generation. You're going to have to deal with those on the client. Okay. So next thing is data design. So the tip for this is to use the best database for the job. The reason is now with GraphQL, you basically have this common interface through which you can communicate with any number of backend data sources. So if you have an old legacy database that may be unfriendly to use from a client application, but it's really good at what it does, there's not as much pressure to move away from that database that does what it does really well. You can put this layer in front of it, and then all of your clients can interface with GraphQL instead of that native database language, and then basically hide and abstract away the fact that it's a really complicated or hard to use API. So here's a few databases that we use all the time. You might have heard of some of them. We've got DynamoDB, which is a great primary data store. It scales really well. It's no nonsense, so you don't have to think about it. You just kind of turn it on and forget about it, and it's going to continue to work, which is really nice. We've got Elasticsearch, which is more for ad hoc and analytical queries. It's generally considered a little dangerous to treat it as your primary data store, especially if data changes and you have to get into re-indexing your Elasticsearch indexes, but it's really good at doing full text search and analytical queries. And then you've got your relational databases, which are great at what they do, easy to relate information, you can do transactions, but then you start to fight them a little bit more once you hit really large scale. So one of the reasons that DynamoDB works really well with GraphQL is that the operations map really well to each other. You can have, here you see the mutations of create X, update X, delete X. Those map really well to DynamoDB, put item, update item, and delete item. You can do the same thing for batch write and batch read. It's really kind of a one-to-one mapping, and it's really easy to use. And then the same for queries. You can do a get item and a scan or a query to return a list. And it's kind of just a really nice mapping. But then one of the problems you find with DynamoDB is, almost everybody I talk to that's coming from a SQL background fights this when they first start using DynamoDB, is that they really just miss the ability to relate information with one another, or relate objects. And the nice part is that with GraphQL, you can basically add some of these relational capabilities to NoSQL just using the same operations that you've always had access to in DynamoDB. But when you're querying it from a client, you don't necessarily have to know that it's coming from DynamoDB. You might think it's coming from SQL because you're able to do relational things, but it's really not. So here's an example of how we might do this. We've got a type user. It's got tasks. A user has tasks. You have a task has an owner or a user. And then all you have to do is add a resolver to that tasks field on the user object that knows how to query a GSI in DynamoDB. And then as you query that from the client, it's going to show up as if it was all one query. The same for the task, the inverse. And you'll see that the user field, you can do a get item against the user table to relate the user with any particular object in the task table. So here's an example of how that might work in practice. Here you can see we've got our get user resolver. That's going to just do a straight get item against a DynamoDB table. And then we've got that tasks field that's going to run a DynamoDB query operation against a GSI that we created on the task index that's indexed by the user ID. And the thing that allows us to do this is what we call in AppSync, we call it the context. It's often called the context or the source in an open source implementation. And it allows you to do, for every single object, parameterize the query slightly differently so that we're looking at a different subsection of the information in the task table, so that we're able to do this query, so get me all the tasks for some user, and then everywhere you're operating on that user, that query is going to work. Whether it's in a mutation, it's in a query, anywhere nested in any other query, everywhere that tasks field is included in a selection set, it's going to grab the correct information. And here's the inverse of that. So you can do a get task. It's going to do the same get item against the DynamoDB query, table, and then the owner is just going to look for that same user object that has the same ID as the context source's user ID. So next, we'll talk about how you might add search to an API. So Dynamo's great at being a primary data store. It's great at listing things. It's great at simple filtering. But it leaves a little bit to be desired when we're talking about full text search or strong analytics. So another common pattern we'll see is that people will add Elasticsearch as a secondary data store to DynamoDB, and then that allows them to get the best of both worlds, where they can have that really strong foundation, and then they can have the rich text search and not be so afraid that their index is going to get corrupted or that their Elasticsearch cluster is going to go down. And then you can always reindex your Elasticsearch cluster from DynamoDB if the worst case happens. So how do you do that? Here's a really common pattern. We do it all the time. It's pretty resilient if you build in exponential backoff and retries into your Lambda function. But what you do is you add a DynamoDB stream to your table. You handle that DynamoDB stream with an AWS Lambda function. And then in that Lambda function, you use Elasticsearch batch index operations to push data into Elasticsearch. This adds, without much overhead and without having to worry about ETL or any other more complex technologies, adds a really resilient pipeline to move information from your DynamoDB tables into your Elasticsearch indexes. And then once you've got the data in your Elasticsearch indexes, you can just query that thing directly from your GraphQL API. And this is how it would work in AppSync, but you could do the same on your own, where you just hit that specific index's search endpoint, and then you can pass in any Elasticsearch DSL query to do it. In this case, we're creating a search tasks by title field that's just going to do a Elasticsearch match query against an index that's parameterized by the argument to GraphQL. And here, you can see that we're using that simple pagination pattern as well. Another common pattern is how to store files. So there's a lot of options here. You can base64 encode a file and put it into DynamoDB and then read it, but then you lose all the benefits of S3 that have been optimized for a long time. So S3 is a low latency, high availability blob storage service. It has CDNs. We can use CloudFront to put a content delivery network in front of our S3 buckets to basically deliver our assets anywhere around the world in milliseconds. And then if you're going to build support for S3 into an application, what I'd recommend doing is only storing pointers to S3 buckets and keys in S3 buckets in DynamoDB, and then allow the client to actually pull down the file, because you're going to see a lot of an optimized data flow and be able to leverage those CDNs to the best of your ability. And here's how you do it. So this is actually cooked into all of the AppSync clients. If you just add this S3 object type to an API that has a bucket, a key, and a region, and you associate that S3 object type with an object in your API, if you pull down that field from your client, the AppSync clients are going to have support to basically go find that object in S3 and load it through a CDN. You do the same for the S3 object input to follow that input pattern, and the AppSync clients will know how to take the file from the device, store the pointer in DynamoDB, and then in the meantime, upload that file directly to S3 using the optimized data flows. And here's how that works. So you can see we have a client. We're calling our create user mutation. We have that single input field, which has a username, and in this case, a profile picture, where we're giving it a bucket, a key, and a region. What's missing here is on the client, you actually pass a local URI as well. And then the client is going to push the data through AppSync, which goes into DynamoDB. And then, meanwhile, it's going to push the blob directly to S3 using your IAM credentials. Here's the inverse data flow where you might want to query it. So you're going to do a get item call. You're going to get a user or get user call, get the user by ID. You're going to get the location, and then that's seamlessly going to pull that blob down from S3 and pull it into your application so that you can use it as if you didn't even notice. So next we'll talk a little bit about Lambda. So a lot of our intention with AppSync was to make it so you don't have to use Lambda, but almost everyone ends up having to use it for some reason or another. It's a really great way of adding compute or just arbitrary compute to a GraphQL endpoint, and it gives you scale without barely any ops. You can also use it to connect any data source. So if we don't support a data source for you, you can use a Lambda. You can even put your Lambda in a VPC to access private data sources, and then connect any other data source that's not natively supported, and pull it into your API. So the tip here is to use a standard event structure. So this is one that's kind of been found through practice. It's just kind of painful to have a different set of data coming to a different Lambda function every different time you call it. So the tip would be to do something like this, where every Lambda function that you use in an API would have the same input structure, and you can parameterize these in the resolvers, such that it forwards your arguments, it forwards your type and your field name, it then forwards the source and the identity so that you can do any authorization checks you might need, and you can associate objects with their parent. So this context.source is the same thing that we used in order to query that GSI to get the tasks for a particular user. And here's doing it again in a query. It's just a different field, nothing changed other than the type and field name. So then the next question is always, do I use one Lambda or two? And there's no right answer, but here's an example of both. So some reasons that you would want to use one Lambda are that you benefit from container warming, especially if you're using a language with a virtual machine like Java or C#. Having a single Lambda, if you have one Lambda, it's going to stay warm more often. You're going to see lower latency from that Lambda, and you're going to see some performance benefits there. The downsides are that you're going to have to write a little bit of routing logic, but the plus side is that it's really not that hard to do. And if you're familiar with writing your own GraphQL APIs using an open source implementation, it looks really similar to what you might do in that case. Here you can see we're building up essentially our resolver function map, where we have at the root level a type name, and then the next nested level is just the field name on that type. And then every value for those keys is a function that returns the value that should be returned by that resolver. And then you can see all you have to do is route it, you call it, pass it back, and then it's going to work great. The cons of this are that you're going to have to implement that routing logic, and you're only going to have one code base. So if you have multiple teams working on it, you're going to have to deal with figuring out how to do that. An alternative is to write a Lambda function per resolver. This is one that people also do, and it works. I've seen it work effectively. The pros are that you're going to have greater separation of concerns. You're also going to be able to deploy resolvers independently of one another, which just reduces the blast radius of what you could potentially mess up in a deployment. But the cons are that if you're using a language with a virtual machine, you're going to see more cold starts, which could lead to higher latency. You're also going to have to deal with n number of repos instead of just that one, which is really just a personal preference. So then to recap, should you use it? It's up to you. I've seen both ways work effectively. Being able to deploy functions independently is really nice, but then I also understand it can be a lot of overhead. And the cold start benefits are real and can really improve your API. So the next topic we'll talk about is real-time data. So this one's pretty cool. It's interesting in that it's something that everyone likes to talk about, and there's a lot of ways to do it wrong. So what are we talking about with real-time? We're talking about GraphQL subscriptions. Subscriptions are the third operation type in GraphQL that allow you to stream information from an API to a device as it happens. And in AppSync, what it really means is a subscription is a reaction to a mutation, and it's event-driven. And then the obvious question that I always hear is, how do you authorize them, and how do you route them efficiently? So we'll talk about that. So here's a simple example. We've got a publish mutation, and we've got a subscribe subscription. This AWS subscribe directive is built into AppSync because AppSync doubles as a broker, a real-time broker, pub/sub broker, and allows you to just, with only this, you'll hook up subscriptions and not have to worry about anything else. We run it over MQTT with WebSockets, so it's resilient, and it's still easy to use. So as I mentioned, there's a lot of ways to do this wrong. It's not that hard to think about how you could do it wrong. If you imagine that you have 1 million clients and a million messages coming through, and you need to figure out for each of those messages, which of these clients do I route this to, and is that user authorized for this message, that would be potentially 1 million checks per message, which would lead you for 1 million messages and 1 million clients to 1 trillion operations, which is not scalable and is obviously a problem. So there are solutions to this. I've heard that Go is a solution to this, which it's not. And then, but the solution that we came up with was 2 parts. First one is to authorize subscriptions at connect time. And the second one is to actually bake the routing logic into the name of the topic, which we'll talk about a little bit. So again, here's another example of a subscription field. It has a single argument in it called chat room ID. and this argument in this field is actually incredibly important. We have a limit of 5 arguments that you can put on any subscription field, and that's because subscriptions in AppSync are not dependent upon the number of connected clients, but actually dependent upon the number of fields that are passed into a subscription field. And we'll talk about this. So first, let's think about what a subscription query really is. A subscription query in AppSync, and people do this different ways, but in AppSync, a subscription query is basically a request to open a topic. When that subscription query is received by the server, it invokes the resolver that's attached to that subscription, and the purpose of that resolver is to authorize that subscription. What this allows you to do is, in this example, we might have the onCreate message with a chat room ID being passed in. We also have the context of who is the caller. We know the identity at this point. So what it allows us to do is go look up in whatever backend data store we're using, is this user able to access this chat room? If he is or she is allowed to access that chat room, then we're going to return a pre-signed MQTT topic name, and then you're going to be able to connect immediately to that topic. The trick is that that topic is actually already parameterized to only yield messages that are related to that chat room ID. And the way that this happens is that every value that you pass in the subscription field gets turned into essentially a bitwise operation for equality. Every time a message comes in, we're going to say, what is the value of the attribute on that object? And then we're going to emit publishes to all of the topics that could potentially have subscribed to this message. So here's kind of how it works a little deeper, is if I have one subscription that's asking for the chat room ID 1 and the logged in identity is authorized to access that chat room, we're going to return topic A. Topic A is mapped to the subscription where the chat room ID is 1. If you added another argument to here, you'd have not just 2, but you'd have topic A, topic B, possibly topic C, and it'd go on and grow as the number of input arguments changes. And then you can see the second one would be yielding topic B. What happens then is when the mutation happens, it not only it runs the mutation and it gets back the object. It then looks at all registered mutations or all registered subscriptions and finds the 32 topics that could possibly be thrown based off of the attributes that were parameterized in the subscription field. So if you remember, I said there's a limit of 5 values that you can pass into a subscription field. The reason that it's 32 topics max is that 2 to the 5 is 32. And that's the maximum number of topics that we might publish to for any particular mutation. Now this is pretty neat because what it does is it essentially makes it so that our subscriptions are no longer dependent upon the number of connected clients. Our subscription publishes are dependent upon the number of arguments that you pass into your subscription field. If you only have 1, then it's only going to be potentially passing to 1. So next we'll talk about some rapid development techniques. So when I started, I said we've been working on a new set of client frameworks and tools called AWS Amplify. And that encompasses a number of projects. There is the AWS Amplify CLI, which is a really great way to generate and quickly scaffold projects and deploy them to the cloud via CloudFormation. And then there's also an Amplify framework that makes it really easy for you to consume the applications that you develop using the Amplify CLI and, in general, any GraphQL API. We also have a new project called the GraphQL Transform. That's an open source project that was released with the Amplify CLI that it's all about allowing you to think about your application and your data in terms of the data model without necessarily thinking about the infrastructure that's necessary to make it run. And we'll see a few examples of this. And last, it includes cool tools like CodeGen. So if you have an AppSync API and you want to generate code for your iOS or Android app that are strongly typed and work with Swift or Java, we'll actually go and generate those types for you and make them work really well with Amplify so that it also works with, for example, the S3 support that I was mentioning earlier. So here's an example of what the Amplify CLI looks like. The way that it is broken out is there are a number of categories. Categories include things like auth, storage, which includes both DynamoDB storage and S3, analytics, which creates pinpoint endpoints, API, which will allow you to create not only AppSync endpoints, but also API gateway endpoints as well, and a number of others. From the CLI, it's a really guided experience. I'd really recommend trying it because as you type these things, it's really going to guide you through what do you need, what are the smart defaults, and we've baked best practices into those. And then at the end, all you have to do is run Amplify push. That's going to generate a bunch of CloudFormation documents. It's going to upload it to the cloud, and then you're going to be ready to go. So then Amplify has, as I mentioned, the support for AppSync. And the way that we support AppSync and Amplify is through the GraphQL Transform project that I mentioned earlier. What it does is it allows you to declaratively define your application's data model using GraphQL SDL, and that's it. You don't have to worry about defining the key schema of your DynamoDB table. You're not worrying about GSIs or LSIs. You're just saying, I have users, users have posts, and posts have comments. And then we're going to wire that all up with best practices so that you can quickly prototype and generate those APIs for your applications. It comes with a number of pre-built transformers. A transformer is essentially a class that defines a directive. And then every time that that directive is found in an input document, that class is called and invoked in order to do some amount of manipulation on essentially your CloudFormation template context, and then you iteratively build things from there. The cool part about this is that you guys can actually write your own. So it comes with a number of them. We have model, auth, connection, versioned, and searchable. But we've had customers that have built their own to do specific Lambda use cases, people that have written their own resolvers to call out to specific internal REST APIs. And then from your input, you just have a really easy to use interface. And here's kind of what it looks like. So if you type Amplify add API, it's going to ask you, do you want to build a GraphQL API? You're going to say yes. And then it's going to ask you, do you have a schema? If you have a schema, you can just copy and paste it. If you don't, it'll give you a few tips on how to get started. And it'll actually open up the schema.graphql file in your text editor of choice. And then there you can just start writing your GraphQL schema. Here you can see we've got a simple post. It has an app_model directive on it. App_model, what it means is we're going to create a DynamoDB table for you. We're going to create a data source. We're going to create an IAM role that's scoped down just to talk to that DynamoDB table. We're also going to code gen CRUD resolvers for you. So you're going to get create, update, delete, get, and list. And then it's going to be all wired up so that just with these 4 lines of code, you've got essentially a couple hundred lines of CloudFormation that are all ready to go. And then voila. This is essentially what you get. This is what your API would come from that simple type definition. It gets a little bit more advanced than that though. So here you can see an example of how we'd use the auth directive. So that we still have type post. Our type is a model. A model is going to be stored in DynamoDB for now. We have this auth directive. And what the auth directive does is it allows you to add authorization to the CRUD operations that are generated by the transform. In this instance, what it does is it actually code generates authorization checks depending on how you parameterize these rules that are put into your resolvers, and then depending on the data store, will hook up the authorization check. For example, in DynamoDB, if you're trying to put an ownership authorization rule on a update operation, it's actually going to create a DynamoDB update condition expression that is going to make sure that you cannot update that object unless you're actually the owner of that object as designated by the logged in user credential. And then that's all you have to do. You don't have to worry about writing resolvers. You don't have to see velocity. It's really easy to use. You type Amplify push, it's up in the cloud, and you can start using it. Here's another example. So this one is my favorite. It's at connection. This is going to allow you to easily associate objects without worrying about how they're associated at all. So you say type post, it's a model. You have type comment, it's also a model. You've got then corresponding connection fields that have the same name. So that name is how we join fields in 2 different models. So in this case, you can see that the comments is a list of comment. The other pro here is you don't have to worry about the connection types. You just say it's a list, and we understand it's a list and that you're going to want pagination, so we're going to add that pagination for you after you've deployed it. In this case, you can see it's going to create a one-to-many relationship between our posts and our comments. So comment has us as a single post, and our post have many comments. So what that's going to do is it's actually going to create a GSI on the comment table that's on the where the hash key is the post ID, and then it's going to implement the query field resolver on the post comments field, and then the inverse, it's going to implement the get item resolver on the comment post field. With this, that's all you have to do. You click push, and you've got it. Here's an example of how you'd query that, just to make it ring. So here you can just do a get post, ID, title, comments. You've got your pagination parameters in there. You can get the first 10 things after some cursor. And you never had to write a single line of CloudFormation. You never had to open up the DynamoDB portal. And you never had to see velocity. Here's one more cool tool that has been really useful as of late. We've added support for Android and iOS, so you can create strongly typed clients as well that are generated from your API. And then it has support for iOS, which is Swift, Android for Java, TypeScript, Flow, and even JavaScript, although it's not strongly typed. All right, next topic. We've got offline data and Delta Sync. So we've had support for offline for a while. What it is, we'll build normalized caches on clients, and then we'll persist them in various offline stores. If it's in React Native, we'll use async storage and SQLite for Android. But what we've added now is support for what we're calling Delta Sync. And what this is it allows you to only download what's changed between going offline and coming back online. So the way that works is you're going to have a base query. Your base query is going to hit the main entity table. In previous examples, we were using type post. Your base query is going to list that post table. You can use queries. You can pull down whatever information you need. Then you've got a subscription query. So after you've made your base query, you would open a subscription that's then going to start streaming information and merge it into your offline cache so that while you're online, you're always up to date. The subscriptions are going to push the information down. It's going to be in your offline cache. The client's going to read from the offline cache, and it's going to show and be responsive. But then what happened before is if you went offline, there was no way to easily say, I only want to get the things that changed since I last synced. So where this comes in is we've added support for what we call the Delta query. The Delta query is going to hit a different table. That table is basically going to be a transient table, a temporary table that only has the information that's changed. It's going to use DynamoDB time to live attributes in order to flush information that's old, that we don't need anymore. And then you're going to be able to hit that Delta query against that Delta table to only get the information that's changed without overfetching. So here's how that works. So last week, we also released a new feature called the pipeline resolver. A pipeline resolver or previously we had resolvers. Resolvers were functions that were able to go hit any one data store. Pipeline resolvers basically move it a level up, and you're now able to chain multiple resolvers in unison on a single field so that you can hit multiple data sources in one resolution for a field. This is super useful for authorization. If you have some authorization credential that lives, if you want to only be able to create messages in a chat room you're a member of, for example, you'd be able to first make sure that you're a member of that chat room and then authorize to create the message. We also use it for Delta Sync. With Delta Sync, we would first create the post in the entity table. We'd then also create an entry in the Delta Sync table. We'd set an expiration date that is what is the longest amount of time that we want this object to be in the Delta table. And then we're going to order that thing by timestamp. And then once you're reading it, this would be your base query. Your base query is going to hit the entity table. It's going to read all that information from the entity table into your offline cache. You're hopefully only going to have to do this one time. And if you don't only do it one time, you're only going to have to do it next times when you want to completely update your cache. From there, you'll then use the list deltas query that's going to go and read against that delta table and find all the records where the timestamp is greater than or equal to the last sync time. So I only want the records that have been created since I last synced from my individual client app. Different users might have different last sync times. And such that the expiration date is greater than now, so that we're not getting data that we meant to be flushed out. There's actually support for this in the AppSync client. So you can give a base query, a subscription, and a Delta query, and all of this is going to be happening behind the scenes for you. And then the transform will eventually support kind of generating the stuff really quickly on your behalf. So another thing we're going to talk about, so CI/CD, this is a super hot topic, something we hear a lot from customers. And the good news is that yesterday we released an entirely new service. It's called the Amplify Console. It's now a cloud service. And the Amplify Console is a really no-nonsense CI/CD platform as well as web hosting platform. that's going to allow you to host web apps with blue-green deployments and atomic deployments right off the bat. If you're using the Amplify CLI, it's going to be extremely seamless. You're going to be able to, whatever you can do with Amplify CLI, you're going to be able to do with the Amplify Console, and it's going to be able to add CI/CD really quickly. So one of the cool parts about this is the atomic deployments. So atomic deployments, the problem that we're trying to solve is if you're pushing front-end code and say you're hosting that front-end code on an S3 bucket, that S3 bucket, when you're pushing it, you might not finish the deployment, and if you're pushing to the same bucket, you might get your application stuck in an unsafe state. Say you were able to push the first half, but you weren't able to push the second half, then the deployment fails for some reason, your application's likely going to be broken. With this, what we actually do is we use Lambda at edge in order to, when you do the deployment, it'll push into an entirely new bucket, and then at the time that the deployment finishes, it uses Lambda at edge in order to change the routing so that it just starts pointing to your new bucket instead of the old one. It also has support for GitHub, Bitbucket, GitLab, and AWS code commit as your push triggers. So there's no more worrying about how do I push my information to S3. You just you use a build spec, you put it in your repository. You're able to then just use your normal developer workflow. Every time you push to GitHub, we get a webhook. We're going to build that. We're going to deploy your front end. We'll deploy your back end. And then we'll update the hosting using the atomic deployment. Another nice feature that this comes with is the Amplify CLI is launching a beta for multi-environment support. This has been one of the most common asks we've had where not only do we want multiple environments such that I can have my dev and my prod, but we have teams that are larger than one person that are trying to share code between each other, and if you have to always operate off the same cloud infrastructure, you're going to run in and step on each other's toes. So what this does is it allows you to have essentially a branch per environment, and you can even do multiple branches. It's a little bit different, but you would be able to have your master branch or your local development feature branch. You could then associate that local development feature branch with Michael's sandbox. When I then run Amplify push, it's going to parameterize everything so that it's specific to my sandbox. I can then go to the Amplify console. Say I'd have a dev branch and a prod branch that are kind of our CI/CD, our continuous flows. When I push or merge my feature branch into that dev branch, there's going to be another environment that's managed that's actually hosted on the Amplify console, and that will push all of the changes into that branch, and it'll update that stack and push it to the cloud. And then as you merge that dev branch into the prod branch, it's going to do the same thing and allow you to move changes between feature branches and then kind of beta branches into your production branches with a lot more confidence. And it allows you to share code with your team, which is really nice. So then in terms of operations and monitoring, there's a few things that I'd recommend you do. The first is there's support for CloudWatch in every Amazon AppSync API. All you have to do is toggle a switch, and then we'll start streaming basically resolver and per field logs into your CloudWatch account for you. You can then go and set up your own alerts. You can set up alerts for 4xx, 5xx, latency, error messages and logs, and all these nice things. And it's something that you kind of just have to go to the settings page and turn it on. And we find that it's kind of hidden, but I really recommend that you put it on and turn it on. And then as I said, you get 4xx and 5xx metrics as well. And then we'll have more for that in the future. And then in addition to that, I mentioned the analytics category in Amplify. This is going to be a pinpoint API that you can use for really powerful client logging and analytics. That's a little different than the service, but it's a nice way to add analytics to your client application so you can get things like session time, number of page visits, and things like that. Another cool thing that you can do, and this is something that you're now able to do because of pipeline resolvers, is you're able to basically add resolver auditing for particularly sensitive resolvers. And the way that you would do that is you would create an audit function. So I mentioned that a pipeline resolver is now basically a way to run in series a number of different what we would previously have called as resolvers, but now there's a new concept called AppSync functions, which are essentially a single distinct operation against a data source. And you can create a single audit function that would know how to push a log into your own DynamoDB account, or you could stream it into some other monitoring portal or time series database using HTTP resolvers. And with that single audit function, you can then add that audit function to all of the resolvers that you care about. And every time those functions that resolver is invoked, you're going to get that audit log showing up in your data store so that you can do your own custom auditing without having to worry about changing every single resolver and or running everything through a Lambda function. Next, a few tips for testing APIs. I'd break it into 3 categories of things that you can do. One is integration testing. There's also unit testing, of course. But for the APIs, integration testing, this would be something that you would trigger upon your CI/CD workflows. With the AWS Amplify Console, we actually ping out a CloudWatch event that you can then attach a Lambda function to, so that every time an event happens in your CI/CD flow in the console, you can run your integration tests and make sure that that thing didn't break. Another really common workflow for this is to basically detect breaking changes and to prevent breaking changes. And if you look at the GraphQL JS library, there's a nice utility that can just take any 2 schemas and then perform a diff and tell you which of those changes could potentially be breaking. And then you can add your own logic to alert on those and have various workflows in order to stop those from flowing into production. The other is just to have canaries. So canaries it's the canary in the coal mine. These things are running all the time, every few minutes. They're just sitting there waiting for something to go wrong. When something goes wrong, you alert, and then you get notifications using SNS using email or any other way. And then another one that's particularly interesting is basically to just automatically create test suites using various tools. So there's some projects on GitHub that allow you to do this. It's not that hard to do it yourself. But you can basically auto-generate fuzz tests against any GraphQL API just by introspecting the schema and then throwing everything that you can think of at it and just do it randomly. So this is nice for basically finding the edge cases that you wouldn't otherwise test with integration tests, and it's something we see a lot of people doing. So last topic is schema governance. So this is one that is also a very common question. It's something that I find happens in evolutions. Almost everybody we talk to starts with a centralized schema governance kind of plan, and then they always think, how do I get to that point that we're doing decentralized schema governance? And to back up, when I'm talking about schema governance, I'm basically talking about who is the gatekeeper to decide what schema changes get pushed through to production. And when you see a lot of these companies, they'll start where there's one team that has ownership of a repository that has that big schema.graphql file or a number of schema.graphql files in it. And then they are the ones that will say yes or no to changes coming in. And often that'll happen through a series of pull requests. So then if you're a team that's downstream or you're a client team and you need a new field, you'd basically go fork that repo, you'd create a change, you'd create a pull request, and then it'd be the ownership of that team to go decide, is this okay or not? The alternative to that is decentralized schema governance, which takes a little bit longer to get right, but it's really it's the golden ticket. It allows everyone to have control of their own subgraph, and there's actually features built into the GraphQL language itself to allow you to do this, and the main one being type extensions. So it would allow you'd have your base API, where the root of your API defines the root of the type query, your type subscription, your type mutation, maybe any of your user types or anything else. And then that'd be basically the root. And then any other teams that need to change anything would basically be able to go add their own schema declarations that use the extension types API so that you could add fields to your query or your mutation or any other type in your API. But the hard part of this is getting it right generally requires a more advanced CI/CD and kind of integration flow. So if I'm going to make a change, I want to be sure that it's going to work. And if I'm responsible for the service as a whole, I don't want that downstream team to be able to go break something where I don't necessarily have the way to say no. So then a lot of these things that I mentioned before generally come first, and teams work towards this because it does become a bottleneck once you get sufficiently large that the one team that's managing your schema can't really keep up with the speed of the rest of the organization. So that's it. thank you for listening. I really appreciate it. It looks like we have a few minutes left, so I'll open up the floor for questions, and we can do a little QA. And follow me.
Generalized question. Is there a timeline when API gateway features, like rate limiting, things like that in GraphQL?
So there's no definite timeline yet. Throttling and other rate limiting is coming in the future, but I cannot, unfortunately, give a date necessarily right now. Yep.
When you're dealing with your current limit on a resolver, are there any techniques, because you can have multiple resolvers to resolve, say, a query, are there any techniques you can use to not get that particular?
Wait, sorry, one more time?
So resolvers have a one-day rate limit and the response size.
Mm-hmm.
And have a query that runs multiple resolvers. Any one violence in one day, or an aggregate violence, any techniques to avoid helping you do that?
To avoid hitting the file size limits or response size limits?
Spread the cost, make multiple limits.
Gotcha. Yeah, so his question was there's a 1 megabyte limit per resolver and techniques in order to avoid that and get around that. I mean, it's a good question. I mean, the limit is a limit. You could, as you said, kind of break down that thing into multiple sub-resolvers, but then the downside of that is you'd be running more. You can also just ask AWS to increase the limit, and we can see what we can do.
Follow-up question for the offline clients, any plans of having encryption across?
On the clients themselves. So I'm not aware of that, of the roadmap for that, but that's not to say it's not being worked on. I can definitely follow up and see, but we don't have any definite timeline for that.
How are you guys getting around, as you develop larger and larger systems,
Mm-hmm.
being able to have those sub-teams be able to not deploy out the entire solution, but just their sections?
Yep, so schema management is something that we're aware of and that we'll likely see some changes in the future, basically being able to break things up into more modular pieces of not just one schema, but multiple schemas, and then also versioning and modules, essentially. So it's, yeah, again, no timeline, yeah.
You discussed an idea earlier with Amazon and Amazon will stream the Lambda, then Elasticsearch.
Yep.
This is, I understand this was for Graph API, but what if we can use this solution for the problem of scanning DynamoDB with large amount of records? We are facing many issues with Dynamo, with big data, big numbers of data. We have same tables, we write and read. So we can use this idea to maybe make another interface for reading records other than making Dynamo just for updating and inserting.
So you can definitely still continue to use Dynamo for reading data. I think it depends on what you're trying to query by. Can you give an example of what your query pattern would be?
Many feeds, it's real-time data.
Mm-hmm.
Okay, so we have like table of thousands, hundreds of thousands. So at any time we might need to read with any feeds. If you are asking about the search criteria, so it's not specifically for the index.
So you basically want ad hoc queries on a Dynamo table?
Yes.
Yeah, so I mean, one of the downsides of Dynamo is that when you're deploying Dynamo tables, you need to think about your query patterns beforehand. So this may be not an answer that you're looking for, but if you want to be able to find one field, you want all the records where a particular field is equal to X, you need to think about that beforehand and then create that GSI or the LSI in order to be able to do that, or else you're going to be basically querying that sparse index.
There's another solution to this, which is as you're putting information into Dynamo,
Yes.
you can stream it out to Kinesis if you're looking for real-time data.
But
Kinesis streams will allow you to query real-time across.
the problems of Kinesis, it has double issues. Sometimes double.
So
We have very critical data.
would you be able to use SQL? Would you be able to use RDS? SQL? Aurora?
Yes, Dynamo was a first solution. We went from in the first place. But now we are in the situation that we are adopting Dynamo in our use case.
Yeah, I mean, I think that it is a use case driven decision. Like if you're trying to do ad hoc queries against a Dynamo table, you're going to run into some problems at scale because, I mean, say if you don't have a GSI on a field and you want to just find all the records where some value is equal to n, then you're going to have to scan that entire index.
Yes, exactly.
Right. So the solution to that is think about your query patterns beforehand and then build that GSI into the table, and then you're able to get the efficient query. But if you're looking for the ad hoc query that you just want to be able to, on any field, do any sort of computation and figure out all the values where A is greater than B or B is greater than C, then you're really going to be probably looking at a different database, something like Elasticsearch.
If we are specifying the fields, what would be the solution?
How many fields do you have? If you only, so there's a limit of 5 GSIs per table, and if you have 5 fields that you know you need this query by, then you can create a GSI on that field. And what that does is only records where, well, basically only records where that field is filled out go into that GSI, and then you're able to query it by a value. So if you want to know where the name is equal to Michael, then you'd be able to hit that GSI and find only the records where the name is equal to Michael. But if you are just arbitrarily saying, oh, today I might need the name, but then tomorrow I might need some other attribute, then you're going to have to go add another GSI to that table in order to efficiently query that index. Otherwise, you're going to be stuck with the table filter or the scan.
Okay, how we do handle the limit of Lambda 5 minutes, which is Dynamo is very big.
So let me jump back. So are we talking about the search, right? All the way at the beginning. So are you asking now, how do you do the streaming into Elasticsearch? No, sorry. Looks like it's stuck. Let's see. So with this solution, you're saying this solution would not work?
No, I was asking if this solution can solve my problems with reading from Dynamo with different criteria. This is my question.
Yeah. So this will definitely, I think, work for your solution. Is if you're going to stream information from Dynamo into Elasticsearch, Elasticsearch has a much richer DSL querying language. So it'll allow you to do really complex queries over really large data sets, and also allow you to do really advanced analytical queries so that you can do aggregations and counting and stuff like that, where Dynamo won't allow you to do that kind of stuff. Mm-hmm.
My second question was, with Lambda direct with Dynamo, we are using in other use cases Dynamo, Lambda functions to read from Dynamo. We are facing many issues, performance issues with the limit of timing of Lambda, because many big data in Dynamo, it might take above 5 minutes, which is
To move from DynamoDB into Elasticsearch, you mean?
no. For any other.
Anywhere, just to read it.
Yeah. Lambda with Dynamo,
Mm-hmm.
there is no performance. You know, if you have a Dynamo table with hundreds of thousands records,
Mm-hmm.
and you need, for any reason, for Lambda to fetch some data or scan or find for whatever, we have critical issues with performance because sometimes it might take above 5.
Right. So I think again the answer is if you're using a scan, scans are going to read the entire index. So a scan's going to read the whole table every single time. You should be adding GSIs on the fields that you care about, and then when you add that GSI, you're going to go straight to those records, and it's going to you're no longer going to miss records. It's going to be able to give you exactly the data that you need.
And that's across any NoSQL database, not just Dynamo.
Right. It's just a pattern of how NoSQL works, because Dynamo is essentially a giant distributed hash.
Do you have any advice around managing a schema when certain APIs don't have necessarily well-defined responses? So as an example, looking at a customer activity history, they might have been looking at the website, they might have been looking at using the mobile app or something like that. How to best be able to handle querying for that data, but again, when you have a schema.
So basically, when you have unstructured data, That you want? Yeah, so I have two answers to this. One is that something I've seen kind of in the GraphQL community in general is that there may be a need for a map type. A map type where you'd think of it almost like how you can do a map type in like TypeScript, where you can say the key is of type X and the value is of type Y. That may be coming. It's just that's going to take a long time because the spec is a slow-moving thing. The other way I'd recommend it is if you can think about it, instead of thinking about it as a map, you can think of it like an association list. So instead of having just keys and values, you can basically have a key field and a value field, and then you'd be able to either have that be the primary key or have that be an index where the hash key is going to be like the name of the attribute that you care about, and then the value field would just be the value that's associated with it. And then you'd basically be able to get that unstructured data in the form of like an association list instead of as a map. Because then the map would fight the schema, but with the association list, you can just say this is a list of type X, where X is the key value.
Does any integration exist, or is any integration planned to exist for Neptune?
So it's common ask. No deadline, but we know. We also just released support for RDS. So that's a cool one. I don't know if you guys knew, but there's a new HTTP endpoint for RDS, which is pretty neat. So we're one of the first people to be using that. So you can actually directly run SQL queries from AppSync into an RDS instance, and it'll work without having to worry about connection pooling or any of that fun stuff.
Does that mean it works with SQL Server?
It currently, the bottleneck is on what's the RDS team. It's in, I don't know if it's technically GA yet, but it does not work for SQL Server. I believe it's only MySQL now. But I'm sure RDS will be rolling out support for more in the future.
How do you implement caching with AppSync? How does it cache things?
So you mean client caching or like server-side caching?
Both.
So client caching works through basically the client frameworks understand the schema. They build a normalized cache based off of the queries that you're writing. So then you can kind of think as like the key of the cache is going to be like the value or the AST of the query that you're particularly asked for. And then the arguments of that query are going to be taken into account. And it's basically a flat map that then gets kind of stitched together as it builds. Server-side caching, there's no first-class support for what you'd consider like where you'd put like Redis or something in between a database and a API, but there are per request cache in the data loader pattern. So that's something I could talk about more if you're interested.
You mentioned about subscription that you use in MQTT client against like a website. What's the principal difference? How would you describe it?
So it's MQTT over WebSockets. So MQTT is just the implementation of the protocol, but then it's actually communicating over WebSockets. Yeah.
Does the delta sync function you're talking about work for mutations, or is it only queries?
So, well, I mean, the way it works is the mutation would write to the delta table, and then the delta query would read the delta table. So I guess they kind of work together. Yeah.
So generally, all these platforms that do dynamic created tables pretty much just fall down to some scale, right? The scale varies in design, of course. But are you integrating into Elasticsearch automatically to try to have, when they start getting complex, I mean, Jav's going to write a query, it just isn't logical, right? Is it going to handle that somehow, or at what point is it going to just be the dev needs to go down to lower level services that this is using?
So I don't know if I understand the question. So we don't host the Elasticsearch for you.
Okay.
Yeah, so it's all stuff that's...
Use secondary global indexes in DynamoDB is the only thing it can query, right?
AppSync?
You had, what was it, posts and comments?
Mm-hmm.
Right, let's say I want to be able to search for comments by date. So I'm going to have date research comments, I'm going to tie back to user ID. As I start building more and more queries like this, I'm going to quickly run out of 5 indexes.
Right, so you're right.
Devs are just not thinking about the data.
Gotcha. Yeah, no, so I mean, I think you're talking about the limit on DynamoDB indexes, where there is a limit of 5, and that's something that we just can't break. It's the way that it's built up. So basically, if you're going to use DynamoDB, you're kind of given the promise that you're going to be able to efficiently query by 5 hash keys. You can configure those hash keys differently such that you can have different secondary sort keys, because you can have different LSIs as well. So as long as, if you share a hash key, you can have more than 5 indexes because you can have more LSIs, which is a local secondary index. And then, but you're right, I mean, at a certain point, if you need to be able to query efficiently by 100 different fields, you're probably going to be needing to look into an Elasticsearch or looking into a SQL in order to have arbitrary indexes.
This is automatically going to be creating those LSIs, GSIs?
So when I say that we automatically create them, that's specifically referring to Amplify.
Yeah, that's what I'm talking about.
Right, yeah. So, yeah. So you're right. Right now, when we do the connections are implemented as GSIs, and that would be a limit. But there are actually other ways in order to create like the concept of a connection. One example would be like an associative map. So then you can actually store values in the same table with one GSI, and then use that single GSI in order to find all the associated records to do many-to-many. So then we can get around it. It's not implemented yet.
Not us, if we're doing it.
Exactly. So we're looking at it, and we're thinking the downsides are that you lose some of the filtering abilities when you don't do it that way. But exactly, it'll likely be either a new directive or a way to parameterize the connection directive to say, I don't want this to be a GSI, I want this to be a map. Yeah, and then we get around it.
We can take the questions outside. We just have to get to the next.
Sure. Thanks, everyone.